The absolute value symbol, denoted by the vertical bars, indicates that the value of the expression within it will turn to a positive result, even if it's a negative result. If it's a positive result, no change occurs. So for example, if we simply have a numerical value, the absolute value of 2, that evaluates to, well, not surprisingly, just 2 again. But if it's absolute value -2, that turns to a positive sign. So the value of the result within the absolute value expression becomes positive. And that's true even if we have a more complicated operation. 2 minus 5, first step, evaluate the expression within the absolute value symbol, and that turns out to be -3 in this case. And the absolute value expression applied to that turns the result positive. And the answer is +3. Likewise, absolute value of -4 times 6 evaluates to -24, and the absolute value of that becomes +24. So let's suppose we had the following equation. The absolute value of x equals 2. What would the solution be? Well, we actually just saw that already. It could be +2 or -2. So essentially, x could equal +2 because the absolute value of 2 is 2. Likewise, x could equal -2 because we also know the absolute value of -2, as we just saw, evaluates to 2 as well. So we effectively have a positive and a negative case we have to solve for. So in each instance, we have to take the value of the expression equals the positive result, and the value of the expression equals the negative result. How might we look at that graphically? Our solution set is the point 2, x equals 2, and the point x equals -2 on the number line. And one way to think about the absolute value is the absolute value of the distance from 0, in this case, is 2. And that's true in either direction, whether you're going positive or negative. You'll have a distance of 2 from the 0 to your solution set, and that is to -2 and 2. Let's take the case where the absolute value of x minus 5 equals 10. Just as before, we'll have to solve the positive and the negative case. So we'll have to set up two equations. X minus 5 equals +10. And then likewise, x minus 5 equals -10. Because we know if that expression, x minus 5, evaluates to -10, that result will be 10. So we have to set up that equation for the positive and the negative equalities. And let's begin to solve them. Looking at the first one, I will add 5 to both sides of the equation. The result is 0 here. X plus 0 equals 10 plus 5, which is 15. Or more simply stated, x equals 15. And if I were to graph that, I'll take that right over to my number line and indicate x equals 15 on my number line as a solution. And then I have to solve, again, the negative case where that expression evaluates to the negative value on the other side of the equation. So again, I'll try to isolate my x by adding 5. The result is x plus 0 equals -10 plus 5, or -5. So the solution to this, more simply written, is x equals -5. And I can in turn go back to my number line and graph that point on the number line. What I'll notice graphically, my solution set is an absolute value of 10 units away from +5, the opposite of the figure within the absolute value expression, added or subtracted to the x, the variable. And that absolute value distance of 10 up and down will be my solution set. So one interpretation of this equality is that my solution set for x is going to be an absolute distance of 10 away from the point plus 5. Let's quick take a look at another example. Continue with that interpretation of the absolute value equation. I believe the solution for x will be an absolute value distance of 5 away from the central point, -2 in this case. So I believe the answer should be from -2, moving 5 in the positive direction, should yield a solution point of +3. And then moving 5 in the negative direction should give me an evaluation of -7. And let's check those solution points by solving the equations. So again, I know I'm going to have my positive solution case, x plus 2 equals 5, and my negative solution case, x plus 2, even if it evaluates to -5, that in turn, through the absolute value, becomes +5. So I have to solve two cases again. And in this case, I will isolate my x by subtracting 2 from both sides, and I'll simply get x equals 5 minus 2, which equals 3. Sure enough, there's my solution point. Let's look at the negative case. Again, I'll subtract 2 from both sides, and I will get x equals -5 minus 2, which equals -7. And there, sure enough, is my other solution point. So that's a useful tip to know and understand conceptually what's happening on the number line. You're an absolute value distance away from the right side of the equation, and the central point is denoted by the figure added or subtracted within the absolute value expression in the variable we're looking at. Let's take a look at another. The absolute value of x minus 3 equals 2. Again, I'm going to look at the 2 as the absolute value distance away from the central point plus 3. So graphically, I will start with the central point of +3, and I'll move an absolute value of 2 away from that, which should be 5 in the positive direction, and then 2 in the negative direction should take me to 1. And my solution points will be 1 and x equals 5. So let's solve and make sure that's correct. The positive case, x minus 3, evaluates to 2. And then again, our negative case, x minus 3, evaluates to -2. Again, because we know the absolute value of that -2 result will still be a +2, which solves our equality. Let's add 3 to both sides. X equals 2 plus 3, or 5. Sure enough, there's our solution. And add 3 to both sides here again. We'll simply get x equals +1. And there you have it. You have both solutions, 1 and 5. Let's take a quick look at another. In this case, we have a slight twist. The absolute value of -x plus 3 equals 1. I'll still make a similar interpretation graphically. Will be an absolute value distance of 1 away from the opposite of the minus times the +3. So in this case, I'll interpret that essentially as if it were x minus 3, and my central point will be the opposite of that. So I'll get a central point of 3 and an absolute distance away from that of 1. So if that interpretation graphically is correct, that means my solution sets should be 1 away from 3 in the positive side, and then 1 distance away from 3 in the negative direction, which should be 2. So I should be looking at a solution set of x equals 2 and x equals 4. And let's check that by solving the equation with our positive and negative equalities. So minus x plus 3 equals 1. And likewise, we know minus x plus 3 could equal -1. So in this case, I will subtract 3 from both sides. Get minus x equals 1 minus 3 is -2. divide by -1 on both sides, and positive x will equal positive 2. Sure enough, we have one of our equalities. Likewise, let's solve the negative case. Minus x plus 3 equals -1. I'll begin by subtracting 3 again from both sides. Divide through by -1 to isolate a positive x value, and that results in x equals positive 4. And that's our second solution point on our number line. So hopefully at this point you've learned two things. One, to solve for the positive and negative case for every absolute value equality, which is a little different than a normal equation. You have two solutions to look out for, and how to interpret the absolute value equations, at least simpler ones such as this, on the number line graphically. In fact, if you get good enough at that, you can just simply eyeball the absolute value equation and know graphically what your solution set should be without even solving the equations. I do suggest you go through solving both equations, the positive negative case. And lastly, I ultimately suggest you always take your result, and this is true for absolute values and all solutions in general, and plug them back into your equation to make sure your solutions are correct. Because with any equation or inequality, you could have one solution, many solutions, or possibly even no solution. So you want to be sure that you did all your calculations correct and interpret your results. So if I went back and looked at it, minus 2 plus 3, where x equals 2 in this situation, the absolute value becomes the absolute value of plus 1. First, I evaluate the expression within the absolute value symbols, and then I apply the absolute value, and of course that's 1. So that one checks. Likewise, I want to try the x equals 4 case. So the absolute value of minus 4 plus 3 is 1. And within the absolute value expression, that evaluates to -1, which I know in turn evaluates to 1. So that checks. Both solutions do check back within our original absolute value equation. Let's take a look at another one with a new twist, in the case where I have a coefficient of x that is different from 1 or -1. In this case, graphically, I would interpret this as my absolute value distance is not simply 5, but it's 5 divided by the coefficient, or 5 halves away. So that would effectively be my distance from my central point, and minus 3 becomes positive 3 for my central point, but in this case again it's not just plus 3, but it's 3 divided by that coefficient of x, 2 in this case, and that's my central point. So let's apply this graphically. A distance of 5 halves in either direction, that becomes 8 halves, or 4, and in the opposite direction, it becomes 3 minus 5, or minus 2 halves, otherwise -1. And my solution set should then be x equals 4 and x equals -1. And now let's go through our tried and true solution of the positive and negative cases. 2x minus 3 equals 5. And the negative case, 2x minus 3 equals -5. So here I will add 3 to both sides. 2x equals 5 plus 3 is 8. And I'll divide by 2 on both sides to isolate my x, and x equals 4. Sure enough, we have one of our solutions matching. Let's look at the negative solution case. Again, add 3 to both sides. 2x plus 0 equals minus 5 plus 3, which works out to minus 2. Divide by 2 on both sides, and we get x equals -1. So again, our interpretation was correct. Around the central point of 3 halves in this instance, dividing by that coefficient of x, or a distance of 5 halves in either direction. Let's take a quick look at another example. So in this case, I'll graphically interpret this as the solution set for x is going to be a distance of 10 divided by my coefficient 5, or 2, away from a central point that's going to be the opposite of the minus 5 within the absolute value expression. So that's plus 5. But in this case, also divided by my coefficient 5, which equals 1. So that again will be my central point and my distance in either direction away from that central point. So central point of 1, distance of 2 in either direction should give me negative 1 is 2 to the left, and positive 3 solution points is 2 to the right of 1. So now let's solve and verify that's correct. My positive case and my negative case set up as follows. I'll add 5 to both sides. 5x equals, in this case, 15. Divide by 5 on both sides. And x equals 15 divided by 5, or 3. Sure enough, we have one of the solutions. Let's look at our negative case. Add 5 again on both sides, and we'll get 5x plus 0 equals minus 10 plus 5, or minus 5 at this point. Divide both sides again by 5, and our result will be x equals minus 5 over 5, or minus 1. So again, our graphical interpretation worked, and we might just want to go back and check again. It's always a good rule of thumb whenever you're solving equations, plug your results back into the equations. If they work, you know you did your calculation correct. If they did not work, you know you made a mistake somewhere along the way and something is wrong. So in this case, let's say 5 times 3, plugging in 3 for x, minus 5, the absolute value, and that will evaluate to 15 minus 5, so that's 10, and sure enough, that just equals 10. And likewise, I could try 5, plugging in negative 1 for x, is minus 5 minus 5, so that equals the absolute value of negative 10, which also in turn evaluates to 10. So our solutions do check. We can understand them graphically, and we solved for our positive and negative case. Make sure you understand all three concepts. Let's take a look at a slightly different case. How about 2x minus 5, the absolute value of, equals x? Well, the graphical interpretation of this is a little less obvious. So let's move on to our first positive and negative solution case. 2x minus 5 equals x. And in the negative solution case, we know 2x minus 5 must equal negative x, because even the absolute value of negative x will evaluate to x. In this situation, I'm going to try and eliminate the x from the right side of the equation, so I'll subtract by x on both sides, and in turn get 1x minus 5 equals 0, at which point I can add 5 to both sides to get a result of x equals 5. And that gives me one solution. Down here, on the negative case, I'll add x to both sides, the result of which will be 3x minus 5 equals 0. Add 5 to both sides. 3x plus 0 equals 5. X equals 5 divided by 3 after dividing by 3 on both sides. And that would be my second solution case. Let's try another example. Again, I'm going to have my positive case solution and my negative case solution for every absolute value equality. So that's simply 3x plus 5 equals x minus 1. 3x plus 5 equals the opposite of x minus 1. So first things first, I'll subtract x from both sides. And then I'll subtract 5 from both sides. And divide by 2 on both sides to isolate my x and eliminate that coefficient. X equals minus 3. On my negative case, let's just multiply out the negative 1 in front of the parentheses and expand that expression. A minus times the parentheses or an expression is essentially minus 1 times every element in that expression. So minus 1 times x is minus x. Minus 1 times minus 1 becomes plus 1. And that's the result of expanding our expression. At which point I will add x to both sides to eliminate my x on my right side and isolate x over on the left side. 4x plus 5 equals 0 plus 1. Next, I'll subtract 5 from both sides to isolate the x, result of which will just be 4x plus 0 is 1 minus 5 or minus 4, and x dividing by 4 on both sides becomes x equals negative 1. And that is my negative case solution.